Record. Well, for the first time since the very first day of class, we are completely in line with the course outline, which is kind of an interesting feeling. I'm not used to this. And this lecture set is actually pretty short, so I shouldn't jinx it because usually I say that and then we don't finish it, but I'll say that I'm confident we're going to finish it, even though I guess I shouldn't have said that. Okay, we are in lecture set 11. We're going to study the one-way ANOVA procedure today. So basically, in this lecture set, we're going to be looking at another hypothesis test, no confidence interval, and we are going to learn about another type of distribution called the F distribution. So the F distribution is the distribution of the test statistic from the ANOVA procedure, which means that basically once we get to step 4 of this hypothesis test and we have to build the critical value or find the p-value, we're going to be using this F table instead of the t table or the normal table or the chi-square table. So this is the 4th table that we are going to learn about. And it serves the same role as the other tables that we've learned about in the class. And actually, just to kind of further give us a little bit of finality to the course, this is the last table that we're going to learn about, which again kind of emphasizes the fact that we're getting quite close to the end here, and our time together is fleeting. Okay, so with that being said, the first part of the lecture set will basically just be a few examples of how to use the F table. The F table is the same as a chi-square table or a T table. It's just that the layout is slightly different because we now have 2 different degrees of freedoms. Following that, we're going to talk about what the ANOVA procedure is and when we would use it. Basically, the ANOVA is an extension of the two-way t-test or the 2-sample t-test. So we use ANOVA to test for a difference among among 3 or more means at the same time. So we had 1 sample hypothesis tests, 2 sample hypothesis tests, and the ANOVA is a general set or a general test when you have 3 or more means and you want to know if there's a difference among any of those 3 or more means. All right. Oh, and I sent out an email last night. I'm just going to make a note here. I sent out an email last night. On the first page of assignment 5. Okay, so degree of freedom calculation, use formula on first page of assignment 5. On the first page of assignment 5, there's a couple of different notes, and one of the notes says, for the degree of freedom calculation on this assignment, please use the following formula, and it gives you this giant formula to compute the degrees of freedom. So I've had a few students send me solutions to the question to check work, and so in the lecture, I use the minimum of the 2 sample sizes minus 1. And on the final exam, it's perfectly fine to use this formula because the formula given on assignment 5 is very tedious to use and it would take up a lot of time. But on the assignment, use that formula because it's in the instructions. So if you've been working on these questions, make sure that you adhere to the instructions that are given on the first page of the assignments because every assignment has these sets of instructions. And actually in the instructions on the first page, it also tells you how to treat the degrees of freedom. So in our rule of thumb, when we're working with a degree of freedom calculation is if the degrees of freedom is not given explicitly on the table, you round down. So always round down when you're using a degree of freedom for the T table or the F table or the chi-square table. Okay, that's the rule that we use in those different situations. So for example, if your degrees of freedom was 103, you would round down to 100. If your degrees of freedom was like 247, you would round down to 200 on the t-table. Okay, so always round down with degrees of freedom. And for the two sample test, which I think is question number 2, use the formula that's given on the first page of assignment 5. The reason for this is because we want the solutions to match what we do in the R Commander work, and R Commander uses this formula. So if you don't use it, you're going to have a mismatch in solutions, and then you might not get the same conclusion because of the different degree of freedom. Okay, so make sure you adhere to those instructions. Any questions about that? Yeah, you can do it on step 4. You can do it before you start the test, whenever you want. I guess step 4 would be the most logical point because that's where you use degree of freedom for the first time. But my comment there was just like, you could also have like a preliminary setup before you do the assumptions where you compute the DF, and that would also be acceptable. So it doesn't really matter where you place it, but step 4 would be a very logical part to put it in. Any other questions? If anyone has to drive today, be very careful. I was on my way to school and I had to turn back because the roads were covered in ice and I couldn't brake. No, it's going to be a little bit of, it's going to be this lecture set and a bit of the next lecture set. Assignment 6 should be out soon. I was talking to the to John, who is writing it, and he said that he was just fixing up a few typos either Tuesday or Wednesday. So it'll be out soon, and then I can confirm, but it'll definitely be this lecture set, and it might be a little bit of the next one, but it's a shorter assignment because of the turnover time. All right. Okay, so first thing, F distribution. The F distribution has the same shape as the chi-square distribution. So the F distribution is also a right skewed density curve. It's a continuous curve. The lowest value it takes on is 0. The highest value it takes on is plus infinity. The F distribution has 2 degrees of freedom, which we can call the degree of freedom numerator or first degree of freedom, or we can call this the degree of freedom denominator or the second degree of freedom. Most often I just use first and second degree of freedom, but I will show you explicitly what these are in terms of the calculation later. And once I show you what these are in terms of the calculation on step 3 of the hypothesis test, the numerator denominator definition will make more sense. But for now, right skewed, same shape as a chi-square, but it has 2 degrees of freedom, df1, df2. All right. So as a result, when we're actually using the F distribution to conduct hypothesis tests, we again don't have any concept of being two-sided. So just like with the chi-square, we're always doing our tests in the skewed tail. So these are just some different descriptions of what a F distribution looks like. The point of these illustrations is to show you what the different degrees of freedom control. So I'm going to give you an idea of that. Oh, sorry, one sec. I didn't have the my usual thing prepared here. So there's 5 different F curves on this slide. So I'm going to show you what happens basically as you change the first or the second degree of freedom. So the black curve here is an F curve on 4 and 4 degree of freedom. Okay, so just for reference, the way I'm writing this is F, DF1, DF2. So 2 degrees of freedom, the first one goes first, the second one goes second, right? Okay, so the black curve is an F on 4, 4. The blue curve is an F on 4, 10, and the red curve is an F on 4, 30. So you can basically see that what happens when you change the second degree of freedom is the peak of the curve is coming up and the tail is coming in, right? So the second degree of freedom kind of controls height, if you will, of the peak. Okay, so then we also have a green curve. Now with the green curve, what we're going to do is change the first degree of freedom. And then we have a yellow curve. I'm going to use this color to try and make it a little more clear. We'll change the second. So you can see that when you're changing the first degree of freedom, what this does is kind of push the peak over to the right. So the second degree of freedom is kind of the up and down of the peak. And the first degree of freedom is the left and right of the peak. Okay, so first is horizontal, second is vertical. So we're going to use F curves in the same way that we use the normal curve, the T curve, and the chi-square curve in the context of hypothesis testing. So we're going to use the F curve to find critical values or to find p-values for the ANOVA F test. So in order to do that, we need to have an F table in which we can reference to find our critical values or our p-values. The F table has 8 different pages associated with it. So the way that the F table would work would be pages 1 and 2 would be beside each other, sort of on a horizontal plane. So you would read page 1 and 2 across. Page 3 and 4 would fit in underneath them. So it's kind of like if you imagine a 4x2 grid, like a 4x2 contingency table. So you have 4 rows and 2 columns. It would go 1, 2, 3, 4, 5, 6, 7, 8. So you would read across and down. So as you go across, your DF numerator gets bigger. And the DF numerator, again, is the same thing as DF1, right? So this is DF1 gets larger across. And then similarly, DFD, which is DF2, gets larger as you move down. So the thing with the ANOVA with the F tables that's a bit annoying is that you have to kind of go from page to page to try and find the right combination of your first and second degree of freedom. Right, so for example, here's my first page. So I have 1 through 9 in DF1, and I have 1 through 8 in DF2. When I move to page 2, I now have 10 through 120 in DF1 and 1 through 8 in DF2. When I go to page 3, now you can see the increase in DF2. I'm going 9 to 16 in DF2, 1 to 9 in DF1. So again, it's sort of like 1, 2, 3, 4, 5, 6, 7, 8, moving down and across. All right, so in terms of working with the table, it is basically a chi-square table and a T table with 1 extra degree of freedom. So we're going to match DFN to DFD, and then our significance levels are here. So instead of it just being a two-way system, where we match the degree of freedom to the significance level, we now go DF1, DF2, significance level, and then across. Okay. All right, so we'll look at some examples here. Question 1, what is the value of F360.05? Okay, so this is telling us that in the first spot, we have DF1. In the second spot, we have DF2. And in the third spot, we have alpha. Okay, so we have 3 degrees of freedom in spot 1. We have 6 degrees of freedom in spot 2. And we have a significance level of alpha. So we go to page 1 of our table. We have 3 degrees of freedom in DFN. So again, DFN is DF1. We have 6 degrees of freedom in DFD. Okay, so this is DF2. Right, and then we have a significance level of alpha, 0.05. So then we match 3, 6, 0.05. So 3, 6, 0.05, and that gives us 4.76. Okay. Example 2, what is F830.01? So this is going to be the same idea. So now we have 8 in the first spot. I'll use a different color here. We have 8 in the first spot, 3 in the second spot, 0.1 was it, or 0.01? 0.01. Yeah. Okay. So 8, 3, 0.01 is right here. Okay, so that's basically how you would find critical values using the F table. Any questions on that? Okay, what is the probability that F is greater than 10.62 at 3, 6 degrees of freedom? Okay, so this is going to be an example of finding a p-value. So we're going to sketch our right skewed curve. Again, the curve starts at 0. This case, we have 10.62. And we want to know, well, I'll use the p-value color that I usually use. And we want to know this part here. So we want to know the size of this shaded area to the right of 10.62. Okay, so the probability F is greater than 10.62. We have 3 and 6 degrees of freedom. Okay, so we go back to our F table. We're going to be using 3 and 6 degrees of freedom and 10.62. So here's 3, here's 6. Okay, now what we do is we take the block of numbers that's associated with those 2 degrees of freedom. So we're going to use this block of numbers here because they are the block at 3 and 6. And now what we're going to do is just determine where does 10.62 fall in among this block. Okay, so our lowest value is 3.29. Our highest value is 12.92. Our value is 10.62. So you can see that 10.62 is going to be in between these two numbers here. $10.62, right? So we're in between 9.78 and 12.92. So that means that the area to the right of our value is between 0.01 and 0.005. Okay, so we can then say 0.005 is less than this probability is less than 0.01. Okay, and this would be the solution to the problem. So it's the same concept of range building that we saw with the chi-square and the t-table. It's just that the way that we work with the table is slightly different because of the construction of the table. Any questions? Oh. Okay, what is the probability that f is greater than 4.5 at 6 and 8 degrees of freedom? Okay, so this is another example of finding a p-value. So we start by sketching our curve. We mark down where our value is. So here's 4.5, and we want the area to the right here. Okay, so we want to know what is the probability f exceeds 4.5. Okay, so we have 6 and 8 degrees of freedom in this case. So we're going to go back to our F table. We're going to match 6 with 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. Okay, so we're working with this block here. Our F value is 4.5, so that sits in between these two numbers here. Oh, sorry. 1, 2, 3, 4, 5, 6. We're working with this block here. Our F value is 4.5. So that sits between these two numbers here. So we're between 0.05 and 0.025. So we would say 0.025 is less than, this probability is less than 0.05. Okay, so those are two examples of finding critical values using the F table and two examples of finding p-values using the F table. So these will be the techniques that we use in the hypothesis test that we're going to study now. Does anyone have any questions? Okay. So what we're going to do now is learn how the one-way ANOVA technique works. Let me just go over this. Okay, so as I had mentioned before, one-way ANOVA is actually a general extension of the two-way hypothesis test. So you'll remember that with one-way hypothesis tests, we were asking a question about the value of the population mean. So we would say things like, is there evidence that mu, the single mean, is greater than some number, less than some number, different from some number? In the two sample hypothesis tests, which are what you're working on assignment 5, you're asking questions like, is mu1 different from mu2? Is mu1 larger than mu2? Is mu1 less than mu2? Right? So those would be illustrations of the kind of questions you're trying to answer on assignment 5. With the one-way ANOVA, our goal is to make a global comparison among 3 or more means at the exact same time. So for example, on slide number 8, we have a data set where 5 strains of a cultured bacteria that cause staph infection were observed for 24 hours, and the total bacteria counts for each strain were counted. So we have strain A, B, C, D, E. For each strain, we have different bacteria counts. And the goal of this particular, or the question that we want to answer is there a difference in the average bacterial count across all of the strains? So we want to answer that question using one test where we're testing for equality versus a general difference between strain A through E at the exact same time. So instead of testing for a difference between just 2 and comparing all sets of strains until we've enumerated the entire set, we're going to do the entire test at once. And that's the purpose of ANOVA. Okay. Okay, so on slide 9, I'm just reiterating the same idea. So we want to use one global test to determine if a difference exists among all 5 strains at once. Now, in order to do this, what we're actually going to do is compare 2 types of variation, which is why the procedure is called an analysis of variance. So ANOVA actually stands for analysis of variance, but we are using the variations that we are going to define momentarily to test for a difference among the means. So again, the one-way ANOVA, even though it has variance in the title, is actually a test about the population means. Okay, so again, same idea. I'm kind of a slide ahead, but analysis of variance is what the ANOVA stands for, using variation to test for difference among the means. In this class, we're going to study one-way ANOVA. It's called one-way because we only have one variable. So in this particular illustration, our variable is bacterial count. So we're only studying one outcome, which is bacterial count across each of the different strains. So because there's only this one variable, it's one-way ANOVA. There's many different types of ANOVA, and they can consider multiple kinds of variables in their setup. So the one-way ANOVA is the simplest kind of ANOVA because it only takes into consideration one variable, and it's a global test for a difference among the means. I also have a note here that the number of levels of the variable is the same thing as the number of outcomes that we have. So we have 5 different strains, so we have 5 different levels. Okay. In the analysis of variance, we have our response variable, or the variable that's of interest to us. So the thing we are measuring. In this particular illustration, we're measuring bacterial count. So that would be the response variable for this particular problem. Okay. Again, the factor would be basically what split the response variable into its level. So the strains would be the factor. This is the same thing as the treatment. There's a lot of overlap in definitions among the ANOVA. The important thing to keep in mind at this stage is we have one variable that's been split into more than two groups. That's the crux of it. So we have one variable that we're measuring, and we want to test for a global difference among three or more means or groups or populations at the same time. All right. So as I had mentioned before, ANOVA stands for analysis of variance. So we are comparing two types of variation in order to make a statement about the population mean differences. Those two types of variation are called the between treatment variation, which is also called the SSTR, so the sum of square treatment, and the within treatment variation, which is also referred to as the SSE, which is the sum of squared error, loosely. Okay, now most of these technical details aren't overly relevant to us right now because we're not going to be performing a lot of tedious calculation. But the point is, you can take total variation in the data set. So basically, if you considered all 25 of the values shown on slide 8 to be one data set, so you didn't consider the strain, you just looked at it as a sample of 25 values, you can compute the variation of those 25 values. And we know how to do this because we already studied the sample variance formula back in lecture set number 3. So we're basically just taking the sum of the squared difference between each observation and the overall mean and computing that value. You can take that quantity and decompose it into two other types of variance. And that's what equation 1 is trying to highlight. So equation 1 is saying you have this total variation around the mean of every single observation in the data set. This can be broken into two types of variation, SSTR and SSE. The SSTR is basically the variation among the groups. So it's how far each of the different groups are from one another. And the SSE is the variation within the groups. So it's a global measure of how far the observations within each of the strains are from one another. Okay, so we have total variation of the whole data set being decomposed into two other types of variation, between group variation, within group variation. Okay, that's the starting point for the procedure. Right? Now, each of those formula have their own computations that are associated with them, and those are shown here. Again, we're not going to dwell on this too much because the assignments typically don't ask us to make these kind of calculations. They're more just like working through the test given what's called an ANOVA table. But for reference, these are the formula that we would use if we had to compute those values by hand for some reason. All right. The test itself. So this is like really what's important to us in this lecture set. The one-way ANOVA hypothesis test is always going to be written as shown on slide 15. So we have H naught, which is the null hypothesis, mu1 equals mu2 equals mu3 equals mu4 equals mu k. So the null hypothesis is a quality among all k population means that you are considering, where k is basically the number of means or the number of levels. So for example, in the bacteria count illustration, k would be 5 because we have 5 different strains. HA, which is the alternative hypothesis, will always be written as not all means are equal. Now, what's important here is that this alternative is not saying all means have to be different from one another. Okay, so this is not the same as mu1 for example, is not the same as mu1, not equal to mu2, not equal to mu3. Not equal to mu k. Okay, that's not what it's saying. All it is saying is that somewhere among the set of means, there could be a difference. So the alternative hypothesis could mean that just mu1 and mu2 are different. It could just mean that mu1 and mu3 are different. It could mean that mu2 and mu4 and mu2 and mu5 are different. There's a lot of different outcomes that fall into the alternative hypothesis. So we are testing a quality of every mean versus at least two means are different from each other among all the means you're considering. Okay. Now, in order to test this hypothesis, we use an F statistic. The F statistic is the ratio of the MSTR to the MSE, where the MSTR is the SSTR, so the sum of squared treatment, divided by k minus 1, where k is the number of means. And the MSE is the sum of squares error divided by n minus k, where n is the sample size and k is the number of means or the number of populations. Okay, so the F statistic is a ratio of two variations, which is why we call it an analysis of variance. And you can see here that the F statistic has degree of freedom 1, which is k minus 1, and degree of freedom 2, which is n minus k. Right? Okay. Any questions? All right. On step 3 of the ANOVA F test, so the hypothesis test that we are learning about, our calculation of the test statistic is typically done through what is called an ANOVA table. So the general ANOVA table is given on slide 16, which is right here. So what's nice about the ANOVA table, and are you asking what is n in MSE? What? I don't understand the question. Are you saying that MSE is equal to n, or are you just asking what n is? Yeah. N is the sample size, the number of observations. Right. Okay, so the nice thing about the ANOVA table is that you add vertically and you divide horizontally. So you'll notice that here we have a summation line. This is telling us that k minus 1 plus n minus k equals n minus 1. So the DF treatment plus the DF error equals the DF total. It's also telling us that SSTR plus SSE equals SST. So for the DF column, the degree of freedom column, and the sum of square column, you can add vertically. Okay, so we can add and subtract in the vertical direction for DF, and we can add and subtract in the vertical direction for the sum of squares. The mean square treatment is found by taking SSTR and dividing by K minus 1. So this is basically telling us that MSTR is equal to SSTR divided by K minus 1. So that means that in the horizontal direction, from here to here, we can multiply and divide. That's the same thing here and the same thing here. Okay. Okay. So for treatment, error total. So for the treatment, the error and the total, you can multiply and divide between the degree of freedom and the mean square. Okay, so depending on what's given to us, and a lot of the time, the kind of questions you'll see are incomplete ANOVA tables where you have to fill the values in. Depending on what's given to you, you can multiply and divide horizontally between those three values, and you can add and subtract vertically between the degree of freedom and the sum of square. So it's just important to keep in mind how the table is constructed, because you can make use of these properties to fill the tables in. And then finally, we have the F statistic, which is MSTR over MSE. So that's just a ratio of the mean squared treatment to the mean squared error. And then the degrees of freedom, again, so this is going to be an F distribution on K minus 1 and N minus K, which is why we typically call it degree of freedom numerator and degree of freedom denominator, because the numerator degree of freedom is the MSTR, which is at K minus 1, and the denominator degree of freedom is the MSE, which is N minus K. That's the idea. Any questions? Looks like it's starting to melt. Okay. So the one-way ANOVA, just like any other hypothesis test, is done in 6 steps. There are assumptions associated with the test, but we're not going to worry about the assumptions in this particular case. So there's 4 assumptions. Once we get to the second year level, we talk a lot more about the assumptions, but the analysis of the assumption requires what's called residual analysis. It's just a bit beyond what we're going to handle in this class. So in terms of running the test, you can assume that the assumptions have been checked. So we're only focusing on the 6 steps of the test. Step 1, state the null and the alternative. So as I had mentioned before, for the one-way ANOVA, the null is equality among the means, and the alternative is difference somewhere among the means. Step 2, significance level. Step 3, test statistic. Step 3 is typically done by building the ANOVA table. So the ANOVA table is effectively how you work through the calculations for step 3, which is to find the test statistic. Step 4, critical value or p-value. This is done using an F table, which we saw examples of earlier. And then after that, reject or do not reject, standard set of rules, and then interpret the test. All right. Okay, so I had mentioned before that you don't really need to focus too much on the calculations because that's not typically what we're focused on at this level for the ANOVA table. But just so you have an example, I provided the calculations to fill in the ANOVA table for the bacterial count illustration. Okay, so basically what I'm saying here is T1, T2, T3, T4, T5. Those are just the totals for each strain. Okay, so for example, T1 equals total for strain A. Right, so this is what you get when you add the 5 values for strain A together. So 104 is going to be the sum of 9, 27, 22, 30, and 16. Okay, so that's 104 or 105. Uh-oh. Uh-oh. 4, 9, 18, 26, 40. No, it's 104. Okay, so then there must be a mistake here somewhere. 7, 2, 9, 16. I'm gonna make this a 14 or 15 rather. There we go. I'll have to go back and check that one of those numbers is off. Anyways, so the point is when you add those 5 values together, you get 104. And theoretically, when you add the 5 values from each of the other columns together, you should get the other 4 totals that are given on slide 18. But I'll go back and check those because I clearly copied something wrong. Okay, so those are our totals. Our sample sizes for each of the different groups are 5 because we have 5 observations in each group. The K is the number of groups or the number of strains. So we have 5 strains, so 5 groups. The sum of the XI is what you get when you add all of the values together in the entire data set. So that's the same thing as just adding the totals together. The sum of the XI squared is what you get when you square every single value in the data set and add it together. All right, and then from there, we're just filling in the formula, which are shown below. Okay, so we're computing SST, SSTR, SSE, MSTR, MSE, and F. And I'm just using the formula that are given here, so the computing formulas, to compute those different values. So again, the purpose of this example is just to give you an illustration of how the calculations would be done if you had to do them by hand. But on the assignments in the final, we're not going to be focused on doing these calculations by hand. We're just going to be focused on working through the F test, filling out the ANOVA table. Those will be our main priorities. Okay, so for this particular illustration, we are testing if there's a difference in average bacterial count across the 5 strains. So we have H0, mu1 equals mu2 equals mu3 equals mu4 equals mu5 versus the alternative, not all the means are equal. So you can see on the null hypothesis, we're simply just counting our number of means and saying they're equal. And then our alternative is simply that they're not all equal. So we can always use the same alternative hypotheses at the same time. What the hell? Where did it go? 9 plus 7. So this is 36, 48. Oh yeah, okay, you're right. So then there is no mistake. Good. Okay. Never compute in public. All right, so step one of the hypothesis is equality among the means versus the alternative that not all the means are equal. And again, you can see for the alternative, we're always using the same thing, which is what one of the nice things about this test. We can always just say not all means are equal in the alternative hypothesis. Step two, significance level. Step three, test statistic. Okay, so we're filling out the ANOVA table here. On the previous slide, illustrations of where these values come from are provided, right? So again, here for DF treatment, for example, we have K minus 1, which is 5 minus 1, which is 4. For DF error, we have N minus K, which is 25 minus 5, which is 20. And then for DF total, oh yeah, this is DRT. We have N minus 1, which is 25 minus 1, which is 24. But you'll notice that these values add together. 4 plus 20 is 24, right? Okay. Now, you can also see our sum of square calculations. Again, these two values will add together to give you 5,260. And you can see the mean square calculations. So 405.1 is 1,620.4 divided by 4. 181.98 is 3,639.6 divided by 20. Okay, so we're dividing horizontally to get the mean squares, and we're adding vertically to get the totals. And then the F statistic is just 405.1 divided by 181.98. All right. So for the ANOVA on step 4, critical value or p-value. So if we take the critical value approach, right, we're going to have an F on 420, 0.05 as our critical value. So this is the critical value. Okay, so we go to our ANOVA table and we want to match 4 to 20. So we're going to go to page 3. It's not enough. Page 5. Okay, that'll work. So if we go to page 5, here's 4. Here's 20. Here's 0.05. Here's 2.87. Okay, so the critical value for this test is the F value on 420, 0.05, which is 2.87. Okay. Our test statistic was 2.226. So we're just outside the rejection region. Okay. So therefore, we do not reject. If we took the p-value approach, okay, we would have F equals 2.226. Okay, so our p-value is going to be this area here. So we're going to have the p-value is equal to the probability F exceeds 2.226. Okay. So we have 4 and 20 degrees of freedom. So we go back to our F table. We're working in this column here. Okay, so you can see that the first value that's listed is 2.25. So we are smaller than 2.25. Okay, so since our test statistic is smaller than the smallest listed value, our p-value is going to be bigger than 0.1. Right, so this is the same idea as with the t-table or the chi-square table. When you're sitting on a boundary, you're either less than the smallest listed probability on the right side or larger than the largest given probability on the left side. So since our test statistic is smaller than the smallest listed value, our p-value is going to be larger than the largest listed area. So we're going to have here, since the probability F is greater than 2.226, sorry. Is greater than 0.1, then the p-value is greater than 0.1. Okay, so regardless of which approach you take, you can see the conclusion is the same. The test statistic does not get into the rejection region, so we do not reject based off of that value. The p-value is bigger than 0.1, so we do not reject based off the p-value. So then we can say, at the 5% significance level, the data do not provide sufficient evidence to conclude that a difference exists in mean bacteria counts among the 5 strains of this bacteria. Right? And that's an ANOVA procedure. So hopefully you see this is fairly easy to follow because we've seen so many F-tests at this point. The big differences here are the first step. We're always looking at different null and alternatives because basically what we're learning how to do in the second half of the class is ask different kinds of questions. So now we're asking about global difference among 3 or more means. Step 3, test statistic calculation, is again quite different because we're in a different scenario and we're using the variation to study the means. And then step 4, we have a new p-value critical value table because it's a different type of test statistic distribution. Okay. Any questions? All right. Okay, so we're going to go through a couple more examples since we still have a little bit of time left. Just very quickly, again, the one-way ANOVA is a test about the population means that uses variance. So it's called one-way analysis of variance because you are analyzing the variances to make a statement about the means. The one-way refers to the fact that there's one variable, and that variable is split across 3 or more groups or levels. The ANOVA procedure does have assumptions associated with it, but we're not going to focus on them in this class because it requires some material that's a bit beyond what we're trying to accomplish here. But in our second year courses, we go into detail on studying the assumptions for this test. When you reject the null hypothesis in an ANOVA, that does not mean every mean is different. It all it means is that somewhere in the system, at least two means are different. So if you're testing mu1 equals mu2 equals mu3 equals mu4 equals mu5, and mu1 and mu2 are different, that's enough to reject the null. So it's not telling you where the differences is. It's simply telling you that a difference exists in the system. Okay, so I have two cumulative exercises, but I'm going to work through one of them with you now, and I'll leave the other one for after. All right, so in the first exercise, we are studying, our variable is the body mass index of women who suffer from, or women, excuse me. We are studying the body mass index of women with osteoporosis. Okay, so these women were given 6-month regimens of denosumab. Sorry, they were given 6-month regimens of this drug, and they were placed into groups where the drug was prescribed at a 0 milligram level. So there was a placebo, 14 milligrams, 60 milligrams, 100 milligrams, or 210 milligrams. Okay, so 5 different levels. Our factor is the dosage. Our variable is the BMI. Okay. All right, so question 1, or no, we don't need this because it's only A, B, C, D. No. Okay, so based off of the data, we're going to answer the following 5 questions. Part A, is this an observational study or a designed experiment? Okay, we have 100, we have however many women this is being placed into 5 different treatment groups. All right, so that would mean 232 women. No, 236 women. Okay, so since the women are being allocated into the different treatment groups, that would mean that this is a designed experiment, right? So we are basically creating an output by prescribing the dosage level to each of the subjects. So this would be a designed experiment. Designed experiment because subjects are allocated into treatment groups to create response. All right. Part B, what is the response variable? So the response variable is what we're actually measuring. So this is going to be the body mass index. Okay. Part C, what is the factor? How many levels does the factor have? The factor is the denosumab drug, and there are 5 levels: placebo, 14, 60, 100, 210. Okay, so 5 levels, 1 factor, 1 response. Okay, part D. At the 10% significance level, is there evidence that a difference exists in the mean BMI for women in the 5 different treatment groups? Okay, so this is an ANOVA test because we're testing for global difference among the 5 treatment groups at once. Okay, so we're going to start off by just saying, assume all assumptions are intact. Step one. Okay, so our null hypothesis is just going to be that mu1 equals mu2 equals mu3 equals mu4 equals mu5 versus the alternative, not all means are equal. On step two, we're going to have our significance level, which is alpha equals 0.01. Annalise, there's 4 assumptions of the test. Again, we're not going to study the assumptions in depth in this course. We're going to, if you want to learn more about them, we study them at the 2nd year level. But if you need to know the assumptions, they're simple random sample, normal population, equal variance, and independence between the groups. Those are the 4. Okay. Okay, so on step 3, we're going to compute the test statistic. So we have treatment, error, total. Okay, so we're going to have degree of freedom, sum of square, mean square, F value. Give myself a little bit more room here. Okay, so this is my ANOVA table. All right, so the degree of freedom treatment is the number of levels minus 1. Okay, so the degree of freedom treatment is 5 minus 1, which is 4. The degree of freedom total is the total number of observations in the study minus 1. So if we were to sum these values together, we should get 236. Yeah, 236. Okay. So now for the total, we're going to have 236 minus 1, which is 235. Okay, the error can be found in a bunch of different ways. If we're going to follow the formula directly, we would have n minus k. So that's going to be 236 minus 5, which is 231. But you can see that 4 plus 231 is 235. So the other way that you could get the error is you could just subtract the DF treatment from the DF total. Okay, now we need to work out the rest of the table. So we are told the SSTR is 98.07661. Okay. And then we are told the sum across the groups of the sample size of each group minus 1 times the variance of each group is 5,586.36. This is actually just a trick. This value here is directly equal to the SSE. So if you compare this formula shown here to the formula given in the table on slide 14, you'll see that that exact same formula is right here. Right, so if you compare this to what's given in the first cumulative exercise, you'll notice that those formula are identical. So this is just kind of testing if you're picking up on those little, well, basically picking up on the formula, I suppose. Right, so that's 5,586.36. Okay. All right, now to get the SS total, all we have to do is add the sum of square treatment to the sum of square total. So we're going to add 5,586.36 to 98.07661. And that gives us 5,684.437. Right. Okay, now to get the mean square, we're going to divide the SS by its degree of freedom. So that's going to give us 24.51915. Okay, and then here we're going to divide. We're going to do the same thing. So we're going to divide the SS by its degree of freedom. 24.18338. Okay, and then to get the F value, we're just going to take the ratio of those 2 degrees of those 2 mean squared errors. So this is going to be, sorry, I'm just going to run out of room, but it's going to be 24.51915 divided by 24.18338, which is 1.013885. Okay. Any questions? Okay, so we can take either the p-value approach or the critical value approach. If we take the p-value approach, we have an F on 4,231, 0.1. All right, so the way that this is going to work is we go to our F table. Now, you'll notice that the largest value we can get on an F table is 120. Here is 4, so we have our first degree of freedom. Just like with the T table or the chi-square table, when you don't have a degree of freedom that's exactly shown on the F table, you round down. So in this case, we're going to have to round down to 4 and 120 in order to complete the question. So we're going to have F4 120 0.1. That gives us a critical value of 1.99. Okay, so we always round down for degree of freedom when we don't have the exact number. So this is going to be approximately F4 120 0.1, which is 1.99. Okay. And then our test statistic is 1.014. So you can see that this isn't going to make it into the rejection region. So we're not going to reject based off the critical value approach. Okay, so then if we take the p-value, right? So here we're going to have the p-value is the probability that an f is greater than 1.014. Okay, so we go back to our f table. We're going to have the same problem here. So we don't have 231 degree of freedom in the second spot, so we round down. So we're going to go 120. Okay, so our test statistic is smaller than the smallest listed value. So our p-value is going to be bigger than 0.1 in this particular situation. Right, so here we're going to have, since the probability f greater than 1.014 is greater than 0.1, then the p-value is greater than 0.1. So we can see from the critical value approach, we're not going to reject. And we can see from the p-value approach, we won't reject because the p-value is bigger than the significance level. Any questions? Step 5. So here we will do okay, and then on step 6, we can say at the 10% significance level, the data do not provide sufficient evidence to suggest that there is a difference in mean BMI between each dosage level. Okay, so effectively we found no evidence to suggest that this drug at different dosages has an effect on BMI. Right. Okay, all good. Okay, so that's one-way ANOVA. That will be on assignment number 6. And assignment number 6 is due a week from Tuesday. So we have assignment 5 due on Tuesday, which was lecture sets 9 and 10. And then assignment 6 is due a week later, which will be this and some of the stuff from lecture set 12, which we will start on Tuesday. All right, so I'll hang around if anyone has any questions, but otherwise have a good weekend. Be careful if you're going out, though it looks like it's starting to melt. And I will talk to you guys on Tuesday.